guys, how are you? Back again. Just want to walk you through lesson 11-1, reading line plots for math. We're starting a new lesson here. It's short and sweet, only 4 lessons. And based on what or where we're starting, I'm guessing you may have had some of this in 3rd grade. Maybe you did, you don't remember it, so we'll do a quick little tutorial, I thought, to get you started. So we are reading line plots, and the I can statement is I can interpret data using line plots. So data, route, tomato. I don't know too many people say tomato, but data or data. I kind of use them interchangeably, so you can't go wrong. But anyway, let's take a look here. This right here is a line plot. Why is it called a line plot? Well, it's made up of a number line, and you plot data on the number line. And we know this is a number line because it does have numbers on it that go in order from least on the left to the greatest on the right. And the 2 arrows here at the end tell us that that number line can keep going in both directions. So this is really just a portion of a number line. A line plot will always have a title that gives you information about the data. So the title of this is Lengths of Fish Caught. And there's also going to be a label at the bottom, which tells you what these numbers stand for. So if I look here, the label at the bottom is inches. So that means that all of these numbers here on the line plot represent inches. 7 inches, 7 3/4 inches, 8 inches, and 8 inches of what? Well, each of these little dots here represent a piece of data. And those dots, as they're telling us, are lengths of fish caught. That means that each of these dots represent a fish that was caught. On some other line plots, you might notice that they're X's, maybe they use icons, but here we're using dots, and I believe for this entire topic, it's always going to be dots. So again, if I'm looking here, I see the number 7 with 1 dot above it. That means that there was one fish, remember each dot represents a fish, one fish that was caught that was 7 inches long. Over here, over 6 3/4 inches, we have 2 dots. That means that 2 fish that were caught were 6 3/4 inches long. And over here, we've got 8 2/4 inches, 1 dot above that. That means one fish that was caught was 8 2/4 inches, okay? So if we look at the question, Emily went fishing. She plotted the lengths of 12 fish caught on the line plot shown below. What was the length of the longest fish caught? What was the length of the shortest fish caught? Solve this problem any way you choose. So right away, I'm thinking, ooh, 12 fish caught. How many dots should I have on my line plot then? You got it, you should have 12. If there were 12 fish caught, that means that there's 12 pieces of data that I need to plot on my line plot. And it's very important to remember that a little later on down the line when you're going to have to create your own line plots. You want to make sure you represent every piece of data. So we're looking for the length of the longest fish caught and the length of the shortest fish caught. So if I come to my number line, I know that this is a number line, and the longest, or the greatest number in this case, is going to be on the right side of the number line. So if I come here and I'm looking for the longest length of a fish that was actually caught, I'm looking for the largest number that has a dot above it. So if I come to the very end of my number line here, I come to 8 2/4 inches. There's 1 dot above that. That is the longest fish that was caught. You might be saying, but wait a minute, what about this one? This one has 3. Doesn't that make it the longest? No, that makes it the most common. That means that the most common length of a fish caught was 8 1/4 inches long. But that's not the longest. This guy beat those 3. 8 2/4 inches is the longest fish caught. Now if we want to know the length of the shortest fish caught, right here, I have to go to the other end of the number line, and I'm looking for the shortest, or the, in this case, lowest number that has a dot above it. So even though 6 is on this number line, there's no dot above it. That means that they caught 0 fish that were 6 inches long. But they did catch 1 fish that was 6 1/4 inches long. That is the shortest fish that was caught, okay? So we've got the shortest fish that was caught, 6 1/4 inches. We've got the longest fish that was caught, 8 2/4 inches, and we have the most common fish caught, which was 8 1/4 inches long. Okay, so we're going to also do some math involved with some of this data too. So if I wanted to know the difference between the longest fish caught and the shortest fish caught, that would be which operation? Subtraction. Very good. I'm talking about the difference. I'm comparing them. So that would be 8 2/4 minus 6 1/4, which would be 2 1/4 inches. So that's just a little bit of math they might ask you to do with that too. Okay, and then if I kind of scroll down, move with me to the look back question. How does a line plot help you see relationships in data? So why do I have to organize this in a line plot, or what's the advantage of doing that? Well, it's kind of quick and easy to look at and to analyze. So I can see real quick, oh, look, I know shortest, I got to go to the left side of the number line. Oh, look, longest, I have to go to the right side of the number line. And I want to know the most common, well, which one is the highest? Which has the most dots above it. You'll notice also that these dots on the first layer are all at the same height. And then if I go up to the next level, all at the same height. It needs to be uniform. So that way you're comparing correctly. Because if I didn't draw this correctly, I might smush these three together so close, and I might space these out so far. And then it would look like this would be more common than that one. So really important when you're drawing. But again, we'll get to that later. Okay, so let's move on to some practice. Okay, how can you read data in a line plot? So take a look at this data chart. Okay, also has to have a title. So now we're moving on to distance walked in miles. Okay, and they made a nice little calendar here for the week. So they have all the days from Sunday to Saturday, and probably they recorded each day. One for a walk, walked for a mile, put a 1 in there. One on Monday, one for a walk, half a mile. Tuesday, 1.5 miles, Wednesday, 1 mile, Thursday, 1.5 miles, Friday, 3 miles, and Saturday, 1 mile. Well, this data chart is great for recording information, but if I want to really make any sense out of this information or look for patterns or kind of compare what day did I walk, what amount, or what was my longest distance that I walked, this is not going to be the most advantageous or the easiest to kind of read. I kind of have to bounce back and forth. So instead, we make a line plot. And just as a reminder, a line plot shows data along a numbered line. Each dot above a point on the line represents one number in the data set. An outlier, here's a new vocabulary word, outlier is any number that in the data set that is very, very different from the rest of the numbers. Outlier reminds me of out in left field for you baseball fans. Right? If you're out in left field, that's also an idiom. Out in left field, what does that mean? It means you are just kind of out of it. You're not really involved, or you're not really knowing what's going on. You're kind of lost. So an outlier is data that's very different, kind of out by themselves, kind of not involved with the other numbers. So here this table shows the distances Eli walked his dog each day for 7 days. How would a line plot help you identify any outliers in the data? So if we scroll down a little bit, and they made a line plot. So like any other line plot, you need to have a title. They took the title here from their data chart, distance walked, and you need to have a label, miles, and we made our number line. How do they know how to make the number line? Well, they look at the data in the data chart, and they say, well, what's the lowest number here? Oh, 1/2 of a mile. So they decided to start with 0. And then what's the longest distance walked? Oh, the highest number here is 3. So that's where my number line has to end. I could go a little longer if I wanted to, but this is all the information that they're using right here. Then we start with Sunday, and I see that I have 1 mile on Sunday. Boop. 1 dot above 1 for miles. And then we've got Monday, a 1/2 mile. Boop. Plot that. Okay, and they plotted all of these numbers on the number line. So now I can read the line plot and see data much more clearly. So for instance, I can see, longest distance walked, 3 miles. Shortest distance walked, 1/2 mile. Most common distance walked, 1 mile. Right there. Okay. And then I can also look and see, well, do I have any outliers? Do I have any data that's different than the others? Look at this amount right here, 3 miles. See how that's different than all the others? This is called a cluster. I don't believe they introduced that word, but this is a cluster because this is the area in which most of the data falls. This number 3 is out here all by himself. I don't know what was going on that day. That was a Friday. I don't know if the Friday fever, just excited the weekend was coming, so they went for an extra long walk, or I don't know, maybe there was some kind of a game going on and he took his dog to the park to see it. Not really sure. We could speculate why the Eli, right? Was his name Eli? Let me go back into the text. Eli, I was right. Why Eli was able to take his dog for a walk for 3 miles on Friday. But we could be talking about that all day, but that's not what's most important, okay? So again, we are able to see the longest miles walked, the shortest miles walked. What was going on that day, Monday? Maybe he woke up late. Maybe he walks the dog before school and woke up late that day. And then most common, okay? Okay, and then convince me says put 4 dots on the line below, so 3 is not an outlier. How did you decide where to place your dots? So if I was going to place my dots on here, I would want to make sure that I have some both over the 2 and the 2.5 to kind of make that bridge, that connection, so that it's not by this 3 mile dot here is not by itself. I wouldn't want to load them up down here because that would still be an outlier. I wouldn't want to line them up above the 3 because they would all still be an outlier then. They'd all be different from the rest of the data. So you'd want to have at least 1 here over 2, 1 over 2.5, maybe put 2 over 2, 2 over 2.5, just so there's some kind of bridge here that connects them. Okay, moving on, almost finished here. Let you do your own work. Question number 1, in the problem on the previous page, how do you know the distance Eli walked on Friday is an outlier by looking at the line plot? So we did talk about that. It's not near any other data. It's kind of out there by its own, on its own, out in left field. If a line plot represented 10 pieces of data, how many dots would it have? It would have 10, exactly. You can't leave any of the data off the line plot. So 10 pieces of data, 10 dots to represent all and every single piece of that data. Okay, looking at 3 through 6. How many giraffes are 14 feet tall? Well, really, I should look at the line plot first before I jump to the question. So we've got a line plot here. The title is Giraffe Heights, and the label at the bottom is feet. That means this means 14 feet, 15 feet, 16 feet, 17 feet, 18 feet. And the dots represent the individual giraffes. So if I ask the question, how many giraffes did they measure? Well, I just have to count the dots. I wonder if that's one of the questions. It is not. So 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like they measured 9 giraffes. Maybe they have 9 giraffes at the zoo. 9 giraffes were measured. So how many giraffes are 14 feet tall? So I come to my line plot, I find the number 14, and I count the dots above it. 1, 2. Each of these dots represent a giraffe. So 2 giraffes were 14 feet tall. What is the most common height? Easy. I just look and say, well, which one has the most dots above it? That's 15 feet because that has 3 dots and no other number has 3 dots above it. So 15 feet tall, that's the most common height of a giraffe. And how tall is the tallest giraffe? Again, since it's a number line, I know I can come to the right side of the number line because it's the largest number. And the largest number with dots above it is 18 feet. So that is the height of the tallest giraffe. And is 18 feet an outlier? Explain. Ooh, let me think about that. Well, we've got 18 over here. We've got nothing on 17, but then we've got 16. Is that out in left field? Is that completely by itself? No, it's not. Even though there's nothing at 17, it's still close to the data. You'd have to be maybe at 19 or 20 to be a real outlier. 18, no. Maybe you're center field. I don't know. But no, you're not an outlier. All right, so I hope that helped you a little bit, and maybe you knew that already and you've already fast forwarded past me. What I'd like you to do is to finish page 593 and 594 on your own. Later on, I'll post the answers so you can check your work. That's all your must do for today. If you have time, you can do the practice here. Some people